Hello, dear viewer. In my other video, a relatively brief explanation, I summarized Craig Reynolds' Boid simulation. In this video, I want to do a deeper dive into the simulation's history, how the rules work and why they were chosen, and potential applications of the simulation. In 1986, Craig Reynolds and several colleagues at Whitney Deimos Productions' Symbolics Graphics Division worked together to produce the original Boids model in an attempt to replicate the emergent flocking behaviors of birds and fish. The model was showcased as an animated short entitled Stanley and Stella in Breaking the Ice, and was shown at Special Interest Group on Computer Graphics and Interactive Techniques in 1987. Two papers regarding the model were published at SIGGRAPHs 87 and 88 respectively. Later, the model was adapted for use in other films, such as animating the bat swarms in Penguin Army in 1992's Batman Returns. Background is neat, isn't it, dear viewer? So what is a Boid anyway? In my simulation, Boids are essentially data structures comprised of vectors, lists, and integers attached to a green triangle. There are a few more bells and whistles under the hood, but to see those you really should check out my GitHub repository. The main thing Boids have are a unique integer ID number, a list containing the visible Boids near them, and two vectors, one for position and one for velocity. The vectors are simply x and y coordinates on a grid, and to move the Boids, we set the new position to be the old position plus our velocity vector. We keep the velocity vector after this addition and modify it so that we're constantly moving. Each Boid is placed in a flock comprised of all the overlapping lists of nearby visible Boids. This neighborhood is plus or minus 135 degrees from the front of the Boid and 2.5 times the height of the Boid, creating a 270-degree field of view extending 50 pixels from the center of the Boid. This comes together such that if Boid 1 is a visible neighbor of Boid 2, and Boid 2 is a visible neighbor of Boid 3, Boids 1, 2, and 3 are all in a flock. Not too complicated yet, right? For each neighborhood, the velocity vector is calculated by a series of rules that forms the heart of the simulation. This produces lifelike flocking behavior to emerge for the entire flock, despite only the neighborhoods being used in the calculation. And now, dear viewer, onto the rules. First up, we have cohesion. This is the tendency of each Boid to move toward its neighbors, kind of like a magnet. In real flocks, you can see Boids far from their flock mates gradually move towards the rest of the flock. This rule attempts to encourage similar behavior for each Boid by averaging the position vectors of all the other neighborhood members and applying that value to the Boid's velocity. This is one of those magic vector arithmetic moments, but doing this works to get the Boids moving toward the center of their respective neighborhoods. Secondly, separation. If cohesion is like a magnet, separation is also a magnet, but with the same poles as all the Boids, so it pushes, get it? Okay, so this one encourages the Boids to avoid hitting each other. That's a much better explanation. This one is pretty clear in real birds too, as they tend to avoid colliding, so we want our artificial ones to do the same thing. The math is roughly the same as cohesion actually, but each Boid only averages the position vectors of the neighbors that are too close to it, then flips the sign of the new average vector to make it push away from those Boids. Once again, vector magic. To punish the Boids who fail to heed this warning, we destroy any Boids that collide. So our Boids are all near each other, not too far, not too close, but if they tried to move together, they would all be heading different directions. This is where alignment comes in. Alignment takes into account the velocity vectors of all the Boids in the neighborhood and averages them in order to determine the average direction of the neighborhood. The important thing is that this rule takes into account the velocity vectors. This is because the direction of each Boid is derived from its velocity, not its position. Once again, this is apparent in real flocks as we see them move in the same direction of their neighbors. These are enough for a basic simulation, but more rules can be added for different effects. Enter goal-seeking and obstacle avoidance. I consider these to be the same rule as one is just the negative as the other. They both add the position of their nearest goal or obstacle to the Boid's velocity, with obstacles having their sign flipped before addition. This is meant to mimic behaviors more readily seen in schooling fish, which is just flocking, but the Boids are fish and swimming. Dear viewer, do groups of flying fish swarm or flock? Back to the deep dive. There are other behaviors used in other simulations, like roosting, leader following, and even hunting and prey rules, but I don't include them in my sim, but other simulations which feature these rules are readily available with a quick Google search. Now, dear viewer, I know you're asking, how is this useful? I mean, it was cool in Batman, but so what? Well, this is useful because it can be used to help model other flocking entities, like drones. In researching my Boids project, I found some mentions of using modified Boid rules to control drones in different applications, like mapping areas from above autonomously. The rules could also be useful for other computer-controlled aircraft. With roosting rules, the simulation could be adapted to control package delivery with drones, or even commercial craft. This is what I find so interesting about simulations like these. They tend to be developed for specific purposes, and then others come and find ways to reuse them in new, unexpected ways. One of the coolest things about computer science is the way old ideas get integrated into new projects to create something completely different. And so, dear viewer, that ends our deep dive into the Boid simulation. I hope this video helps others interested in the simulation understand the rules that cause the emergent flocking behavior to arise. If you enjoyed this video or had a chuckle, please like and consider trying some of my other content. If you like what you see here, please consider subscribing, and thank you for watching.